Welcome to the module on predictions of engineering properties of soil using Excel. In Excel, we will be using the regression models to develop the prediction models. In this particular module, we will be dealing with prediction of angle of internal friction of sandy soil. What is the angle of internal friction? Angle of friction is defined in the context of motion on inclined planes. The minimum angle of incline for which a body placed on it just starts sliding without any external force is what is known as angle of friction or angle of internal friction. Look at the photograph which clearly indicates that till the time the slab is in a horizontal position, the mass which is being placed on top of it at the edge is in a stationary motion with all the force acting directly vertically downwards as mg. So as we lift the bar from the outer side, making an angle with the horizontal as shown in the second stage, where you can see that the angle may be around 25 to 30 degrees, then the mass or the body on which is being placed on top of the bar has started moving. That means this body of mass has taken an inertia of motion without application of any external forces, just because of the inclination of the slab which is being inclined with horizontal to a particular angle. So this is the minimum angle at which the body starts moving without any external force, is what is known as angle of internal friction or angle of friction. That means the resisting force is greater than the driving force for that particular type of body which is being placed at that particular angle. So as the angle goes up, the speed of the motion or the speed of the movement of the body also increases with respect to the horizontal. What is the angle of internal friction? Angle of internal friction or friction angle is a measure of the ability of a unit of rock or soil to withstand a shear force. It is the angle phi measured between the normal force N and the resultant force R that is attained when failure just occurs in response to a shearing stress S. C and phi are two in independent parameters of soil strength with no direct relation between each other. The value C or cohesion comes from the binding properties of the soil grains, and the value phi comes from the friction between the grain to roll on the surface of the soils. If you see a graph of if you see the photograph which indicates a body of mass being placed on top of a sloping surface which makes an angle theta with the horizontal. Now you have a normal force N acting on the body, and then you have a resisting force F acting on the body, and the vertically downward directions motion weight of the body is mg, which acts vertically downwards. The components of this weight on horizontal and vertical directions are mg cos theta and mg sin theta. Now the body will be in equilibrium till the time the resisting force is just equal to or slightly greater than the driving force. That means till the time the value F is higher as compared to mg sin theta, the body will be in equilibrium, it will not move in the downward directions. The moment the value F reduces from the driving forces that is being given by mg sin theta or capital W sin theta, the way we denote these components, the mass, the horizontal plate which is being placed on top of the sloping surface will slightly start moving. So this force, resisting force, will change with the sloping angle. So when the theta is less, the force F will be maximum. When theta is 0, it will be maximum. When theta is slightly moving with 10, 20, 30, 40, then slowly the value of F, the value of resisting force, will decrease. And at a particular angle, when the value of F is slightly less than the driving forces, that means the body is allowed to move on the sloping face without any application of external forces, is what is known as the angle of internal friction or angle of friction of that particular soil. Internal friction is an internal force that resists the movement between the particles of a material. This potential internal movement can be due to either external forces or change in temperature and deformations. The angle of internal friction for sand, if you take a loose sand, it will be between 25 to 30. Theoretically, a pure clay would have a value of 0, and 5 would rise with increasing the sand content and density to approximately 40 degrees for a compacted sandy loam soil. As pure clays are rarely found in topsoil, so the typical value for a clay soil should be in the range of 5 to 10 degrees. The table shows the results of soil stabilization using cement. The percentage of cement varies from 0.51, 1.5 and 2, and the corresponding maximum dry density, optimum moisture contents were being tested using the modified Proctor test method as per IS 2720 part 8. Then using the direct shear apparatus, we try to check the cohesion, the change in cohesion due to the soil stabilization and the angle of internal friction for sandy soil in one of our projects. The idea was to get a relation between the stabilization of the soil with respect to the angle of internal frictions. Now, with this corresponding data, what we have done is we tried to run a regression analysis using Excel. For that, what is being done is you have to go to the data part, data, and then check the tab that is data analysis. Once you check the data analysis, there you will get you have to choose the data analysis tab, which is there on the extreme right, and in that data analysis tab, you have to choose the regression part. Once you are into the regression part, you have to put the input range like Y range and X range. Y is the range which is having your dependent variables, and X is the independent variable. In this particular case, we have entered under Y, we have entered the values related to angle of internal friction, and in the input range X, we have chosen values from independent variable, which is cement, MDD, and OMC for the number of samples which is being chosen. Now, after doing this, what is being observed is you have to tick the labels, because we have included the label in our output, and then we have to tick the confidence level up to 95%. Then the outputs options are available, like you need to define the space where you want to get the output, or you can get the output on a new worksheet or even a new workbook. In this particular case, what I have done is I have chosen the new worksheet. So the moment you click OK, you will get the complete output received at the new worksheet. So you will say OK, and then you will get the output like this, which is already we have taken in the sheet, which is called angle of internal friction regression analysis. Now, in this regression analysis, what is given the output is you will get the R square value, which is 0.983. The adjusted R square value is 0.930. The standard error is 0.310. Observations number of samples are 5. Now, the intercept value which you see is minus of 7.975, and the corresponding multiplication factors for the independent variables, like for cement it is 0.407, for maximum dry density is 19.106, and for OMC it is 0.422. So what we did is we have to use these values in the table to determine the prediction, to run the prediction model or to determine the prediction model. But what we did is, now you unhide some of the columns which are being hidden there. Now what is being shown here is you have the intercepts, which is the output of the regression analysis. Now in this particular case we are not doing anything with cohesion, so we will hide the columns related to cohesion. So let us hide the column related to cohesion. Now this is the standard intercept, minus of 7.9748, and the corresponding intercepts of cement, MDD values, and then the OMC. Now this is the model which is being marked in yellow, like predicted phi will be minus of 7.975 into MDT value multiplied by 19.106, OMC value of the soil multiplied by 0.422, and cement percentage, if at all added, cement percentage multiplied by 0.4071. So by using this prediction model, what we did is we tried to find out the predicted phi value or predicted angle of internal friction for the given sample of soils, and then we check the accuracy by taking the ratios of a prediction versus the actual one, that is H7 divided by G7. And as you see, the predicted ratio or the ratio of this relation is varying between 0.99 to 1.01. Now that means we have developed the prediction model for angle of internal friction phi by showing the variation in cement content, the MDD values, the OMC values, the actual cohesion, and the actual angle of internal friction. If you know these values, by putting these values, you will be able to check what is your percent predicted cohesion values. For example, if cement is say G 0.5%, if you put cement, and 1.9, and then OMC is say 10%, that means your phi value or the predicted angle of internal friction will be 32.747. And if the angle measured is also close to that, that means the prediction is accurate. Now, after developing the prediction model, what we did is we tried to validate these values with some of the actual values which are being tested in the field by varying the cement percentage and then checking the actual phi values in the field. This is again, we have taken the sandy soil only, and in this particular soil we have taken almost 23 samples, and cement content varies from 0, 0.1, 0.2, 0.3, 0.4, 0.51 to and up to 5%. Now what we did is, after using the predicted model, the phi angle of internal friction, the phi model, prediction model, what is observed is, if I use this model again in my prediction models here, so my predicted phi value is 32.94 against 32.82, or my prediction value for the cement of 0.1%, and actual phi value is 34.05, and the predicted value is 33.04. That means my predicted phi value is varying from 0.94 to 1.05. That means there is a variation of almost minus 6% to plus 5% in the prediction of the angle of internal frictions. Now, based on the actual versus prediction, I try to plot a graph which is as shown here. In this graph, when I chosen a range, say plus minus 6% from the actual, so this is The red one is the actual phi value, and the black one is the predicted phi value. And as you see, and the blue line is from the actual, you have taken plus minus 0.6, plus 0.6% and minus 0.6%. So if the black line is within this range, that means my variation of plus minus 0.6% with the variation of plus minus 0.6%, my predicted value of angle of internal friction is meeting the requirement. So out of all the 23 samples, when checked with a variation of plus minus 0.6% from the actual, it is observed that almost all the values are within the limit, as you can see like this. Okay, and if you see a line graph where again you have a variation, say 0.94 is the lower limit and 1.05 is the upper limit, and this is the one is the desirable limit, because when the actual observed is equal to actual, that means the ratio will become 1. So this is the desired line which is required as far as the prediction model is concerned. But from the desired line, my prediction is varying with a variation of plus minus 0.5, plus minus 5% variation. So after going through this, what we have did is we tried to do a sensitivity analysis. The sensitivity analysis, again, nothing but the change in phi with respect to the change in the maximum dry density and the cement percentage. So this is the phi value which is being taken with the model calculations, and for each chain like 1.6, 1.7, 1.8, 1.9 up to 2.3, we are given a range of Proctor value ranging from 1.6 to 2.3, and range of cement percentage 0, 0.2, 0.7, 1.2, 1.7 up to say 8.2. Now, under these conditions, the for a particular range of values, like for example, if it is 0.7, so if my cement content is say 0.7 and my Proctor value say is 2 and OMC is 12, that means my predicted phi value should be 35.582. So if you see the sensitivity analysis, that is 0.7, zero point 0.7 versus 2, this is 35.582. This is the value which is being checked. I will mark it in yellow so that it will be visible to you. This is the value which is being checked. Now that means for a range, for a given range of change in maximum dry density and the change in cement content, you will be able to predict the change in the phi value for a particular type of soil or for a given range of soils. So this is the prediction model which is being developed using Excel, regression model in Excel. So the predicted phi, which is the dependent variable and is generally dependent on the Proctor value, the optimum moisture content of the soil, and the cement percentage, all three multiplied by a coefficient of individual coefficients is all together. So when we call our predicted phi is equal to a mathematical model which is comprising of the intercept, that is minus of 7.975 plus some 19.106 is the coefficient factor which is multiplied by Proctor value MDD, 0.422 of OMC values and 0.4071 of the cement percentage being added. So if the cement added is 0, then this parameter will be 0, and then your prediction of phi will be totally dependent on the Proctor values, that is MDD and OMC. Specific values of angle of internal frictions of some of the soils, if you see, the different types of soils have like GWGP parameters like 35, GWGP, which is sandy gravel with dense, is around 50, well graded clean sand, gravelly sand compacted, if it is, that is under the category of SW under USCS classification system, is 38. Similarly, uniform sand, round grains with loose sand, that comes under the category of SP, is having a specific value of 27, but when it is dense, the value is 34. That means when the soil is being from compacted, that means when the soil transforms from the loose to the compacted, there is a variation, there is an increase in the angle of internal friction. So when the loose soil is having an angle of internal friction, say for sand is 27, the dense or the compacted sand will have a value which is close to 34. Clay of low plasticity, which is compacted, will give you 28. Clay silt of compacted soil, which is under the category of MH, is 25, and so on. And when you see the range of angle of internal frictions for different types of soils available, well-graded gravel, sandy gravel with little or no fines, you will have the range between 33 to 40. Poorly graded soil with little or no fines, that is GP soil type of soil, is ranging between 32 to 44. Sand in general is SW or SP type soils, which is ranging between 37 and 38. The envelope is very small. Medium sand is between 30 and 36, and the dense sand is between 36 and 41. So clay sands are varying from 30 to 40. Loamy sands or sandy clay loams will have a soil frictional value, angle of internal friction of soil, which is categorically defined as SM and SC type of soils, are ranging between 31 and 34. Some other type of soils like inorganic silty or clay fine sands with a slight plasticity, you will have a range between 27 to 41. Inorganic silt, if it is loose, it is 27 to 30. If it is dense, it is 30 to 35. Inorganic clay of high plasticity is 17 to 31. Organic clay of high plasticity, OH, is 17 to 35. Silty loam is 25 to 32. Silty clay is 18 to 32. And if it is clay, it is 18 to 28. Peat or other highly organic soils, if you see, the angle of internal friction phi will have a range between 0 to 10. So to summarize this module, we have talked about the definition of angle of internal friction. We have detailed the analysis of data analysis using Excel's regression model to develop a prediction model so that we can be in a position to predict the angle of internal friction phi for a particular Proctor values. So this model which is being developed is having a variation of plus 5% and minus 6% when validated using some new soils collected from the new data. In the next upcoming models, we will have some more prediction models to cover in. So till then, tune in and thank you very much for watching this video.